anyway, if the students are not there also.
Yeah. Okay, welcome back to the deep learning course. Today we begin a new chapter in deep learning. We are discussing research in deep learning. So we are into the last but one chapter, and today's chapter is titled Approximate Inference. If you turn to the material on that chapter, it might be a little forbidding looking in terms of it's full of equations and so on. What I hope to do is to convince you that it is still an interesting and a very interesting chapter that for you to know about when you are studying deep learning. That approximate inference is indeed a good topic. So I want to start with some intuition before throwing equations and diagrams at you. First of all, you think of a neural network or a deep network as uh, consisting of a bunch of nodes and connections, and we learn a set of values called parameters. So that's all a neural network is. And of course, we think of supervised learning where we have an input-output relationship. But there is also this area called unsupervised learning where we present a whole set of inputs, and the job of the neural network is to learn the probability distribution. And we refer to that as an unsupervised learning problem, that we are not informing it of any output associated with any input. It is just samples and it creates a distribution. And how does it do that is it figures out all the weights. And once the weights are all figured out, what we have basically is a Gibbs distribution, that it consists of a network, an undirected model where there are weights associated with the connections. And as soon as you say that you have variables and weights connecting them, that in turn defines a probability distribution in terms of the Gibbs distribution, that it consists of the product of all the factors divided by the partition function. So essentially we're dealing with a probability distribution of a set of data. So then what are the what are the issues here is, let's say we refer to all the parameters in the distribution as our theta. Theta consists of all the parameters, all the numbers. There may be hundreds, maybe thousands, maybe hundreds of thousands, or even millions of numbers. That's how the machine has understood how your input is all distributed, which ones are more likely, which ones are less likely. You can compute expected values and so on. So, or the average values, you can do that kind of a thing. So now think about it. Supposing we wanted to train this model and we want to present a new example. Let's say it's a network that learns celebrity faces. Well, we bring in a celebrity face and present it as input. What we'd like the system to know is that this is an actual face, and the model should give such a arrangement of pixels, a high probability that this is a good one and not a rare one. And so it has to change its probability for that input. And how can it change its probability associated with that input? You can say, well, needs to change its parameters a little bit. So you're presented an input, it needs to change its parameters. So it gives it a high probability that this is an actual sample being presented. So now the question is, how do you go about figuring out what is the value of the parameter? How should we change it? Well, for that, you need to look at what is the probability that model currently associates with that input. So because we already have some set of parameters, that's how we begin in neural networks. So it's assigning some probability to the input. And we are then asking the question, what should be the parameters that increases that probability? Ultimately, we want the maximum probability. That's called maximum likelihood for a whole set of samples. So we would like to change that. So for that, we need to compute probability for that input. Computing the probability for that input, let's say V is a set of visible nodes and we have presented V. So we want to increase the probability associated with that. And this involves inference, which is what is the probability associated with that input. And we need to calculate that. We basically calculate what is the probability associated with the hidden nodes given that input. and we want to increase that probability. So so inference problem is simply, I present something, calculate a probability. That's what inference is about. And I'm just motivating it, saying, in order to do that, we have to solve this computational problem of being able to compute that probability. So let's just revisit what all I said just now. We are talking about inference. Inference is the problem of going from input to hidden units and output. That is inference. But we are also talking about learning, which is changing the parameters when you present something. Right? So it turns out that learning requires inference. So this is like a cat and, or the chicken and egg type of thing. To get the chicken, you need the egg, and to get the egg, you need the chicken, right? So there is two ways. Same thing here. To be able to learn, you need to be able to infer. And to be able to infer, you need a learned model. So it's both ways. So we're going to learn about approximate inference, which is one of the two problems. And what we're going to talk about is converting that inference problem into a problem of actually learning and into a problem of optimization. So we are going to restate the problem of inference as a problem of optimization and say, well, okay, if you can solve this optimization problem, then you have solved the inference problem. So it's kind of going back and forth between these, and it's an extremely important concept because there is the network. You need to figure out how to do inference with it, and you want to figure why do you want to do inference with it is possibly to learn. Okay, so this is the sequence of things. So we also encounter here the issue of the task of inference itself is intractable. That it's a very hard problem to take an input to the network to start computing, particularly if it is a complicated network. If it is a simple restricted Boltzmann machine, which has got only one layer of hidden units, you can do that in a reasonably good fashion. That's why we got this model called deep Boltzmann machines. Those can do reasonably well. But if you have an arbitrary deep learning network involving convolutional layers, pooling layers, and so on, that is a modern neural network, these tasks are intractable. And why do they become intractable? We will see in the next set of slides that there are several reasons. One is if there are a lot of connections in the network, the so-called clicks in the undirected graphical model become large, and when the clicks become large, the number of possible combinations of all the variables in that click are extremely large. We exponentiate it typically. So it could be because the network connections are like that. Another one is when you have a multi-layer network, when you have layer after layer after layer after layer, the number of combinations again is extremely large. So this again causes a computational bottleneck. So there are several reasons why things become intractable. And that is why we need to not try and use an exact solution. An exact solution will simply say, well, if you want to do inference, just take your input, multiply by the matrix, gives you the next one, multiply matrix, 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 matrix. That would be the standard approach. But this whole process is fraught with computational difficulty. So that's what we're going to examine. Now, we begin with this topic, and there are several solutions people have come up with for this approximate inference in deep learning. Very simple methods rely on simple things like expectation maximization. That sounds like a strange topic coming in inference. Expectation maximization is a method of parameter estimation. And we're going to reformulate the problem of inference as a problem of estimating or optimization. What are the values of parameters that optimize things? So expectation maximization becomes a useful classic technique for that. More famously, there is a whole class of methods called variational methods, which all work with the Kullback-Leibler divergence and variational calculus and so on. We'll look at that. Today, we'll just look at the simpler methods. And one of the things we'll be looking at today would be how do you take an inference problem and convert it into an optimization problem? And there we talk about how a probability distribution can be written in a way such that it gets a lower bound. right? So we say, look, instead of actually calculating the probability you want, can't you live with an approximate probability? So that your problem is reasonably solved. And that is a reasonably good solution. It says that probability that you wish to calculate can be broken into two parts. One is based on a part where you're saying, forget about this complicated probability distribution you're working with, use a simple probability distribution that is not really the real thing, but some version of it, and you can get a reasonable value with it. And but it's not going to be the same as what you are looking for. The difference between the two, in some sense, is going to be measured by what's called as the Kullback-Leibler divergence between the distribution of this simple distribution you have got in mind here, called a Q distribution. So we talk about a P distribution and a Q distribution. P is the real thing. We would like to calculate the real probability P. We're saying, oh, that's too hard. Then why don't you use a simple probability distribution Q, which you can compute easily? You might assume all the variables are independent, multiply all these things. Oh, that's fairly straightforward. And you're going to compute Q. Well, how good is it? I wanted P and you're giving me Q. And you say, well, P and Q are separated by their difference. How different is the Q distribution from the P distribution? Well, the difference can be measured by what's called as a Kullback-Leibler divergence between the two, which is a measure. If I give you one probability distribution over some variable X with a particular shape, and then here is another distribution of the same set of variables with a different shape here, how different are these? What you have to do is move one over the other and do some kind of integration over all the combinations that you have of the two. And that particular way of doing it, there are several ways of doing it. Bhattacharya is one of them. And Kullback-Leibler divergence is what is normally used in most machine learning topics. So how does that help? So we're going to be replacing P with Q. And then there's going to be the Kullback-Leibler divergence between the two, which we don't really need to work with. We can simply say, can't you just work with Q and then infer with it? Okay, so it's going to give you some approximate answer, and we can think about a whole family of things like that. So this is a range of things we're going to do. So we're going to first look at why is this problem intractable? Because of the network connections. And then we go into restating the problem of inference, and finally we will look at this what's called as the elbow, or which is based on the Kullback-Leibler divergence. Okay, so let me share the screen with my slides. Okay, so we have. Okay, I'm not sure if I launched the right one here. Okay, hopefully this is visible to you. Inference as optimization. So that is the topic for today. And this is the first of 5 topics, the task of inference, intractability of inference. Those are the preambles, and then the inferences optimization. Okay, let's begin with what is an inference problem with a deep network. So a common inference problem would be something like this. We have a set of inputs V, and we have set of hidden units H. We're talking about an unsupervised learning scenario, so we don't show an output Y. So here we have inputs and hidden units here. That's the whole network. So when we present samples, we are computing a whole bunch of H's which capture all the correlations between variables and so on. And we refer to all the weights in this network as a set of parameters theta. So we have a model of the joint probability distribution, which is P of V H theta. Okay. Hello? Yes, can I call you back? I'm giving a lecture right now. Yeah. Okay. Yeah. Okay. So I was just mentioning that we have a deep network of this sort. And let's say we want to compute the marginal distribution, which is probability V. So let's say we present a new input and we are asking the question, what is the probability associated with this input? One way to do it is, well, the model represents the joint probability distribution. If you know all the weights, after all, it is exactly a Gibbs distribution, so which has got a model of the entire joint distribution. Of course, there's the issue of partition function. We discussed how to approximate it and so on. So it's possible for us to compute the joint probability P of V comma H under the parameters theta. We'd like to compute the marginal, and by using the sum rule of probability. So if you know P of H comma theta, if you wanted to compute the probability of any new input here, I would sum out the variable H and we get this summation. And why would we want to, why do we want to calculate the probability of some input? Let's say it's a face and we present this face and say, what's the probability of this face? Not such an interesting thing to calculate the probability of a face, but you may want to be doing that because you want to be assigning as high a probability as possible to that input, given all the network parameters and so on. So you want to assign, and of course we want to be doing this for every one of the samples together. So we want to maximize the probability assigned to the data. So such an approach where we would like to maximize the probability for the data given some parameters is called maximum likelihood estimation. We simply say, here is a bunch of data, give me the best possible parameters under some family of distributions, which is given by the network. Just think about it. If we say maximum likelihood estimate for the mean of a normal distribution, we are presenting some samples and we are saying what value of the mean is going to make that probability highest for this set of data. And we can determine it in closed form, which will say just take this sum of the samples divided by the total number. That's the maximum likelihood estimate for the mean of the normal distribution. So that's what we do. We're talking about similar thing here. We're presenting an input which consists of a vector V is coming in as input, and we are trying to say we would like to figure out what's going to maximize the probability associated with that data, and for the values of the parameters. So that's what we're doing. And we have a joint distribution, and from that we want to compute a marginal distribution. And so that now to get the we'd like to compute the marginal. Now to get the bottleneck comes in here. Even though we are given the joint distribution PV, H, to get the marginal distribution PV, we have to sum out the variable H here. Right? And again, why are we doing this? Is to find the theta that maximizes. So we want, if you know the probability for V, we can find the appropriate theta that's going to maximize that V. So that is the reasoning why we are doing this. And it may be too costly to marginalize H, in that this summation is too expensive. So this is one way of motivating what is going on here. Okay. All right. So let me go to this 15.0 here. the motivation again to approximate inference. Okay, I needed to say something about the task of inference. Are you able to see this slide right now? Task of inference.
Yes, sir.
Yeah, you're able to see. It's a task of inference.
The
Okay.
topics, right?
Topics, task of inference. Okay,
Yes,
good.
sir.
I just switched between one PDF and another.
Oh, okay,
And
okay.
I want
Topics are seen, sir.
yeah, you can see topics.
Yes, sir.
Right. Okay.
Yeah.
All right. So let me now formally state what I said in the beginning of today's lecture, that inference is tied to learning. So, you know, when you see simple diagrams about what is machine learning, what is deep learning, they usually say, well, there is this inference, a learning component, there's an inference component. A learning component is to learn all the parameters, supervised, unsupervised. Inference is now you're going to use it. So when some input is presented, you got to be running through the network using forward propagation, right? The other one would involve forward and backward propagation in learning. Inference would involve only forward propagation. Right? So we are saying that the inference is somehow tied to learning. Many probabilistic models are difficult to train because it's difficult to perform inference. Training itself requires inference. Okay. So this is because parameter learning requires inference. The question of what value of parameters maximizes the probability of the observed input output. That's the question. What is the value of the parameters? So what is the value of parameters that maximize the probability? Requires us to determine the output for each input. So you will have to take each input and present it to the network and say what is the output for that. And then of course, once you do the inference, you can now pass it back. So in a sense, the learning part requires inference. The forward propagation requires inference so that you can do backward propagation. We gave a concrete example in the context of deep learning. So again, look at the inference task in deep learning. Given visible variables V and latent variables H, so here we have X as input. We are looking at a supervised learning problem. So we're just illustrating what is meant by inference. So given visible variables V and latent variables H, inference is the task of determining P of H given V or taking expectations with respect to it. So we're saying what is the value over its distribution, or it could be for a specific input. So in the typical feed-forward network, visible variables V are inputs X and outputs Y, and the latent variables H are the hidden units. So we have a relationship between the H given V and H comma V and so on. That's sample Bayes rule. But such tasks are needed in maximum likelihood learning. That is, if you want to figure out all the parameters in the network, it says argmax, which says over all possible values of the parameters, which is we want to maximize this quantity H given V, because that's what the network is computing, H given V. And this is stated here in terms of logarithms because we're talking about the log likelihood function. And the summation is overall or a set of samples, not a single sample. So inference task is needed. So to figure out theta, that is the learning task, we need to do the inference task, which is figuring out H given V, right? So the inference is needed for the need to perform parameter estimation. So many simple graphical models with only one hidden layer, such as restricted Boltzmann machines, are defined in such a way that inference operations like computing PH given V or taking expectation are simple. In a restricted Boltzmann machine with two layers, this job of inference is pretty straightforward. But most graphical models with multiple layers of hidden units have intractable posterior distribution. So RBMs are nice to explain the concepts, but in the real world, when you're talking about different applications, people don't use RBMs, and you use more complex multi-layer networks such as CNNs and so on. So exact inference requires exponential time. So exactly propagating through and calculating the probabilities or expectations you want, that's going to take exponential time, in that if you have n units in your network, it's going to take 2 to the power of n. And if n is even reasonably large, like 200 or maybe 100 or even 50, it's an impossibly large task to be able to compute the probabilities. So we consider here several techniques for confronting intractable inference problems. This is one slide here that says, can you again tell me why is this problem intractable? So this one shows 3 diagrams of networks of the kind that can lead to intractability. When we say intractability, it means the number of operations that you need to perform on a computer is impossibly large, right? 2 to the power of 100 is impossibly large, right? 2 to the power of 10 is 1000, right? And so on, 2 to the power of 11 multiplied by another factor, right? So 2 to the power of 10 times 2, all right. So that's just 2000. But it goes on, you multiply, you double it. That's we've seen this in the COVID situation. If you keep on doubling, you very quickly reach impossibility. It doesn't even have to wait till about 50 steps or 30 steps or 40 steps. It's impossible already. So that is what we mean by intractability. So intractable inference arises due to interactions between latent variables. Really? It's because when latent variables interact, it becomes more complicated. This one is an interesting network here. It's got a bunch of visible ones, the hidden ones here. And what they've done here is they've connected all the hidden units together. Normally, we don't do that. They've connected up here. So this is referred to as a semi-restricted Boltzmann machine. In a restricted Boltzmann machine, there won't be connections between the nodes that are in the hidden layer. Here we allow that, but we don't allow for more complicated connections. And so in such a network, again, there are large cliques of latent variables. So you have all these latent variables together. Here is a clique with 2, 2, and 2. Of course, we connect some more, and we might get a clique of 3. For instance, yeah, this is connected to this is connected to that. I guess this is already a clique of 3 here. All these 3, they're connected to each other. So when the size of these cliques increase, the factors become much more complicated. So that again leads to exponential complexity. Another type of network where we reach intractability is a deep Boltzmann machine, when you have layers connected to layers of a similar kind. Although without intra-layer connections, there are no connections within the same layer, still intractable due to between layer connections. And all of these combinations again make the number of possible combinations, because we remember we would need to compute the partition function, which looks at all possible values of all possible variables. It becomes impossibly large. And another network that is shown here, which is also intractable, is not a undirected model, but a directed model here. And here we have the visible units and then the hidden units. And with this kind of connectivity, if you're familiar with probabilistic graphical models, particularly the directed PGMs and the what's called as a D-separation, we find that there are some interesting configurations that in certain configurations, when the child nodes are known, the parent nodes become connected and dependent and so on. So there are many reasons why intractability occurs. Okay, I needed this preamble before we go back to this set of slides, the common inference problem. So I already showed this. Why we need to do this, what we're trying to compute, for example, the marginal distribution. So now we're going to approach the problem inference as optimization. So we are going to be, so we talked about learning and inference as being related things. Now we're going to look at the learning problem and say, and I mean the inference problem here. Okay, with learning and inference. All right, we're in the inference side of things here. The inference problem itself is optimization. The learning problem clearly is optimization, right? When we studied backprop, when we talked about loss function, minimizing the loss function, we know that learning is an optimization problem. That one we know well. What about this? Inference also can be seen as an optimization problem. And how is that? Approaches to difficult inference make use of the observation exact inference is an optimization problem. Really. So just going from input to output is an inference problem. And we're saying it is an optimization problem. What kind of optimization problem is that? So we'll have to see that. If you're stating it as an optimization problem, then we say, once you state it as an optimization problem, approximate inference is an approximate optimization problem. So it says you don't need to optimize it exactly. You can kind of optimize it approximately and then say, well, you've solved your inference problem for you. So the big trick is, how do you look at the inference problem as an optimization problem, and how do you state that? That is where all this business of Kullback-Leibler divergence and all that come into play. So let's see, constructing the optimization problem. So we have a probabilistic model with observed variables observed variables V and latent variables H. It's a very simple looking connection. It's not quite an RBM, because H could be several layers and so on. We'd like to compute log PV theta. So we want to calculate the probability for any given assignment, because we might need it for maximum likelihood. So as to choose theta to increase it, but it is too costly to marginalize H. So we can't simply take the joint distribution of PV comma H and sum out all the H variables to get P of V. Instead, we compute a lower bound LV theta Q on PV theta. So we're saying, instead of trying to do this marginalization, all right, which is where we have to do the summation, we are saying we're going to have a lower bound that this quantity you're looking for is not greater than something else. And what is this? It's got a parameter called Q. It's got the same V and theta. V is all the visible inputs and theta is the parameters, but it's got a Q also coming into play here. And we say Q is an arbitrary distribution over H. So we have some distribution over H called Q. And this LV theta Q, this particular curly L, is referred to as an evidence lower bound, or ELBO. Next slide will kind of help us explain. Right now it's not clear what is this lower bound. And this quantity, again, it appears in statistical physics. You know, it's kind of amazing how many things that we do in deep learning all borrowed. Partition function itself borrowed from physics. And even this idea of the evidence lower bound is also referred to as the negative variational free energy. We've seen the idea of energy by using a log parameterization of a undirected model. The same kind of thing is appearing here for variational free energy, same thing as ELBO. One can ask these questions. Much of statistical physics was developed over 100 years ago. People like Boltzmann and then Einstein and so on, they were all working in statistical physics over 100 years ago. Why did they think of these ideas of partition functions and even things like lower bound and so on? And they didn't even have computers at that time. So they were trying to figure it out by hand and so on. And they needed an approximation, a quick way of calculating it. And they came up with these ideas saying that partition function is too hard. So we're going to be work with a bound on that. So these ideas were introduced like that. Of course, even today, with all the computing power we have, we still need those because of the exponential growth problem. So I tried to put together this diagram to get some idea of this ELBO, ELBO, which is the evidence lower bound. E stands for evidence, L stands for lower, BO stands for bound, evidence lower bound, or ELBO. So here we have a network whose job is to learn a probability distribution of whatever we are presenting it. It's got the visible units and then the hidden units. Hidden units capture all the correlations that exist in the model, in the data. So that, let's say we are interested in the distribution for a particular entry V here, right? Because we see that why we need to do that again is to figure out the parameters here. So let's say we are interested in the logarithm of PV theta. So this is not just the probability, but the log probability. We take log just to make things easier. Things we can sum things instead of taking products and so on. Logarithm is what we like to use. And that log probability between 0 and this value up here is the exact value. And we say that probability, log probability, can be broken into two parts. One is called the evidence lower bound, which is denoted as LV theta Q. So what we're going to do is, instead of working with this P, we're going to work with a Q, and we're going to compute something that's from that Q, and that's going to contribute this piece for us. And then we say, what is remaining? What is the error between these two? That's going to be the KL divergence between the P distribution and the Q distribution. If P and Q are exactly one and the same, then the KL divergence is equal to 0. It's like, okay, you got it. You know the Q distribution value, then you know the P distribution value. But if you don't know, so if P and Q are different, the difference is expressed by this KL divergence. And this particular KL divergence, KL stands for Kullback-Leibler divergence, will be defined in terms of QH given V and PH given V. So we're going to define it in these conditional distributions, because we are going from V to H, rather than in terms of the marginal V. But that is irrelevant, since we are only interested in the elbow. So it says, although we are calculating the probability of V, and this KL divergence is going to be in terms of H given V for the two distributions. So we're going to have P of H given V comparing itself to Q of H given V. So that is what this part is going to be. So the evidence lower bound is defined to be L of V theta Q, that is the lower bound L. And what is this lower bound L equal to? It is the log of PV theta. That's the full value. That's the full range value that we talked about. And you subtract from it. So we are taking out the upper part we saw in the diagram. That is the Kullback-Leibler divergence between the Q and the P. And so this is, so exactly when the values of Q and P are the same, the Kullback-Leibler divergence is 0, in which case the lower bound becomes equal to P, right? Where Q again, what is this Q here? Q is an arbitrary probability distribution over H here, over H, in this case H given V. Since Kullback-Leibler divergence is always non-negative, one can show that that is non-negative. Kullback-Leibler divergence involves doing an integral over the two distributions. I mentioned that earlier on. Here's P distribution, here's Q distribution. Put it together, and you do some multiplication of these two quantities and integrate over all possible values. And we can show that's always a positive value. Since KL divergence is always non-negative, always has at most the same value as the desired log probability. So this lower bound is has at most the same value as the desired log probability. The two are equal if and only if Q is the same distribution, P. Surprisingly, L can be easy to compute for some distributions. We cannot compute the probability P, but we can compute another probability Q, and that's fairly easy to compute. So that's exciting that we can work with something else. And again, this is the same slide I just had earlier on, which shows evidence lower bound. And you got the same network here. Here's a log probability. Here is the KL divergence. And here is the evidence lower bound. And I just put in this thing at the bottom, reminding you, what is Kullback-Leibler divergence? The Kullback-Leibler divergence between P and Q is defined like this: P of X times log P of X over Q of X. Instead of integral, we have used a summation over all possible values of X. So it's kind of a peculiarly defined quantity, but it's a nice quantity that if P equal to Q, DKL is equal to 0. So its arguments are P and Q. If both are the same, because P over Q becomes equal to 1 and log 1 is equal to 0. So this quantity, and this is summed over all values here, is going to be 0. And so that's going to give you DKL equal to 0. They're the same. Otherwise, it will give you some value, some positive value it's going to give us, because it says KL divergence greater than or equal to 0. So it says that measures how different it is from true distribution. So this is definition of. Now, the canonical definition of ELBO. So that definition that we had about the lower bound is modified here. And we have just stated that lower bound. So we're going to do some algebra. This box shows some very nice algebra, very worthwhile looking at, but I don't think I can lecture through each equation here, but it's very simple and I encourage you to take a look at it. All it is saying is the lower bound v theta q is equal to log p. We just saw that. That's how we defined it. We had the log and then the dkl over here. The next step, it takes the same term here and it notices that by definition of what the Kullback-Leibler divergence is, previous slide had the definition which showed that it was a summation or it was an integral. When you have a summation, remember that summations in probability theory can usually be restated as expectations, right? So this is an expectation with respect to the H, with respect to the Q distribution of H of this quantity, all right? So this is what KL divergence between Q and P of the conditional distributions are. And we're again doing some algebra here, one divided by the other. We are going by PH comma V instead of just P of H given V. So that is Bayes rule being applied over here. And then after you do that, you expand out all the values here. And so now we can state this lower bound is, first term is an expectation, second term is a log, which leads us to this important canonical definition of the lower bound, this is stated here as L V theta Q is the expected value of log of PH comma V and HQ. Why is this interesting? It is saying that lower bound on the probability you are looking for is the expected value over all H of log PH comma V. H comma V is a total joint distribution. So if you're able to get the total joint distribution, compute the average, and there's a term which is nothing but the entropy of this Q. So now we can say that this quantity is easy to compute. It is easy to compute over the network. And so ELBO has this property that's called the evidence lower bound. The evidence lower bound is easy to compute. So again, this evidence lower bound here is stated as expected value of log PHV plus HQ. So it involves, Q is a distribution you can choose, right? You can choose it such as its entropy is easy to compute. And we also have the distribution of the model itself, and this is an expected value of that, and that becomes the lower bound. So inference learning and ELBO, evidence lower bound. Evidence lower bound is a lower bound on log PH comma V. So inference can be viewed as maximizing L with respect to H. And learning can be viewed as maximizing L with respect to theta. Okay, so we have now come up to the point. So why did inference become optimization? That's because we are saying the problem now is finding the best possible Q, and so we want to maximize this quantity because a lower bound. We want it to be as close as possible to the probability. So it becomes an optimization problem. So approximate inference methods, there are different approximate inference methods, which are different ways of approximate optimization to find Q. And the way we do it is by restricting the family of distributions Q. And the perfect optimization procedure is using a restricted family of Q distributions. So what kind of distributions Q does one choose? And so it says you can restrict the family of distributions, or you have a good optimization procedure. And you also, another approach is imperfect approximation procedures that may not completely maximize L. So you may have perfect optimization procedures or imperfect optimization procedures. So you can define all kinds of things to solve something you cannot get exactly. So what are the main schemes for trying to find the best possible Q? One is expectation maximization. It's a classic technique of unsupervised learning, where we're trying to figure out the parameters of a distribution. Another one is map inference and sparse coding. That's another class of methods. And the more famous one is variational inference and learning. Okay, so those are the three classes. So the summary of these approximate inference methods: expectation maximization is a method of learning rather than inference. And in expectation maximization, it's an iterative procedure. There's what's called as an E step, and then there's an M step. In the E step, we maximize the elbow with respect to Q. And in the M step, we maximize the elbow with respect to theta, and allows us to make large learning steps with respect to fixed Q. So we kind of, once we maximize with respect to Q, another time we maximize with respect to theta. So you're trying to maximize with respect to both. So do with respect to one first, and then given that value to the other one. So that's an iterative operation, hoping to find the best possible values of Q and then theta. Map inference involves learn using a point estimate of log PHP rather than inferring the entire distribution. This is to get a value rather than a distribution for PHP. So this is just like saying I'd like to get the most probable output, not the whole distribution. Supposing I have a classification problem where the class could be one of all of the same, so many possibilities. The map method says, give me the thing that you think it is most likely. Don't tell me there is a given probability for every, right? Like a handwritten digit recognition problem, you have 0 through 9. The map approach says, I give you this input, is it 0, 1, 2, 3, 4, 5, 6, 7, 8? Which one is it? So I just give you the most likely value. Whereas a general probability distribution would say, well, the probability of 0 is this, or 1 is this, 2 is this, so on. Map says, forget about all the possibilities, just give me one rather than the entire distribution. So that is an approximate inference method. We just give you one value rather than distribution associated with it. And again, variational inference is the last approach. Okay, so that's primarily what I have for today. Today we have a short lecture on these topics. I introduced what is meant by approximate inference, and motivated it, saying we need to do approximate inference even for the learning problem, and like the chicken and egg problem between learning and inference. And then, okay, once you're satisfied that for inference you need to do that to do learning you need inference. Then we look at, okay, how do you do inference? We're saying inference problem can be stated as a optimization problem. Just like the learning problem is an optimization problem, the inference problem can also be stated in optimization. That is the surprising fact that I mentioned today, because you always knew that the learning problem is an optimization problem, right? With regularization and all that. So that's what mostly machine learning is all about. So we're saying machine learning is the topic, right? Or deep learning. It's all about learning the parameters. There's this whole other thing that is related to it is, once you give me the learned model, how do I use it? Well, you got to do inference. And now we are saying that very inference is very complicated, even though you've learned, even though you have designed the network. And we're saying you need to be able to use it by doing inference. And then we're saying not only that, while you're doing learning, using this optimization, you'll be doing forward prop. You're going to need inference there also. So we're going to need inference during learning. We're going to use inference during testing, right? Inference is needed both ways, during learning as well as during the testing. Okay, we talk about training sets and testing sets. Training sets are used to do the learning. Testing sets are used. How well does it do is this one. But both of them need inference. And that inference, very inference problem for a non-trivial network is complicated. And so we need approximate method. So in a way, this is an extremely, extremely important central topic, how to do it. And to understand how to do inference we have to talk about approximate inference. And to do approximate inference, give me an easy method. Even the easiest method is saying use a queue. What? Use something else. Yeah, you're going to use another queue. And how do you choose that queue? Well, you're going to learn a little bit about Kullback-Leibler divergence between the two distributions. Wow, do I have to learn all that stuff? Integral of pfx times pfx divided by qfx. That's what Kullback-Leibler divergence is. We need that quantity, and that's going to be the difference between the p and the q, and then you're going to infer with this q. Of course, expectation maximization, and these are the other methods that we can use. So what we're going to do on Wednesday is to cover those three approaches: expectation maximization solution, and then we'll also look at the variational methods, which is kind of intriguing approach. We will talk about a method called mean field inference, where you assume all the variables are independent and see how well you can do with that. And then we'll talk about, well, rather than assuming independence, can't you use a probabilistic graphical model for all the variables? Some simple one, need not be the real thing that you can still do inference with. That's interesting, because we're saying instead of doing very simple-minded independent variables, we can have a little bit more complication. And we say using arbitrary PGMs, how can you do inference? So that's that topic. So I just want to leave you with that message. Although it sounds highly mathematical, I think it's an extremely central topic for machine learning, deep learning in particular, because all these intractability issues come up with deep learning. And so that will be on Wednesday, and next week will be the last week of class, and that will be on the chapter 20, which is the very last chapter of research, and that's going to be on generative models. And we've already seen generative models to a large extent, but we'll look at it one more formal time, and maybe some variants of GANs and VAEs we'll look at. That will be a weekly topic for next week. Okay, that's all for today. Are there any technical questions on today's lecture? Okay, I'm not sure whether it's the unmute issue that I'm facing here, but so be it. So that's where we are, and we conclude today. Thank you very much for attending this lecture.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you, Selvi, being the most regular student.
Yes.
Okay.
No problem. Next Wednesday, I will see you, sir. Okay.
Okay.
Bye.
Right. Yeah.